Okay, today we're going to talk about Electrochem 1. So this is the content and these are the learning outcomes for this chapter. All right. So please be familiar with all of them. Some of the learning outcomes are already covered in the topic on redox. Okay, I will not be going into the details. Okay. The focus will be more on understanding how electrochemical cell work, how to do the relevant calculations with regard to standard electro potential. All right. Understanding the limitations, using Faraday's law to calculate, and the relationship of Gibbs free energy to Faraday's law and standard electro potential. All right. And look at some of the possible advantages in developing other types of cells. So here are the references if you want to refer to. Now, so this is just the prerequisite knowledge that is required for this chapter. You need to understand how to assign oxidation state, what is oxidation, what is reduction, and recall the rules in assigning the oxidation number. So here are the rules, and it is a summary of the topic on redox reaction, the rules in assigning oxidation number, and describing oxidation reduction in terms of changes in oxidation state or transfer of electrons. Take note of these two. These are the two important ions. Peroxide ion is O22 minus with an oxidation state of -1. Superoxide is O2 minus. So this is different. Okay. But when oxygen is bonded to fluorine, it forms fluorine monoxide. Because fluorine is more electronegative, you will expect oxygen to be assigned a positive oxidation number. So electronegativity will determine the oxidation number the element in the compound will be assigned with. All right. So the rest of it should be more or less familiar, and do recall how to balance redox reaction. Here are the steps involved for both acidic as well as alkaline medium. Okay, so for acidic medium, you first write the overall unbalanced equation, and then you break down to the oxidation and reduction half equations. You balance the element reduced or oxidized in each half equation. First, balance the oxygen atom by adding H2O molecules on the right side of the equation where you have H plus on the left side. Because the medium is acidic, the H plus is on the left side. All right. And then after you balance the oxygen atom on the right-hand side, okay, there will be oxygen involved because there is oxidation reduction taking place. Okay, then you put the H plus to balance the H in the water, and then you balance the overall charge by adding electrons, and then that's about it. And then you estimate the total number of electron gain, and then you add the two equations together like what you always do for mathematics simultaneous equation. If the medium is alkaline, the steps from 1 to 6 is totally the same. Just that for now, right, if you want to neutralize the H plus, you need to add the required amount of OH minus ions on both sides of the half equation. Okay, because the medium is alkaline, so you need to neutralize or remove the H plus by balancing with OH minus. And then you combine these two, H plus, OH minus, to form water, rebalance the half equation by eliminating any common terms, and equalize the number of electrons gained or lost. And the same thing applies for step 7 and 8 earlier on. So if you need to recap, you can just refer to the redox notes. Okay, there are more examples there for references. So why we talk about redox reaction? Because electrolysis is a redox process. Okay, so this is just a quick recap on what is oxidation, reduction, reducing agent, and oxidizing agent. All right. Now, So when there's a redox reaction, there's always both oxidation and reduction occurring simultaneously. One cannot occur without the other. And this concept of this proportionation should be familiar, where you have the same element undergoing oxidation reduction to form different products. Okay, then we have learned how to construct half equations and how to write back the overall equation using the half equations. So half equation basically just show how the electrons are transferred between the relevant species and make sure that the number of electrons lost must be equal to the number of electrons gained. This is important concept here. So in every electrochemical process, we need to understand that whatever electrons lost at the anode will be equal to the number of electrons gained at the cathode, because they are connected in the same series circuit, which means that the amount of electrons or the amount of charge flow from one electrode to another should be the same. And electrolysis and electrochemistry has many applications, including rusting. Rusting is an example of electrochemical process. Even for processes that you are familiar with, like respiration, combustion, batteries, extractions of ores, electroplating, or even things like making alkaline water in the water purification ionization system. That is also electrochem, the making of alkaline water, or using electrolysis to remove hair from your body is also an electrochemical process. Okay, so there are many real-life interesting applications related to this concept. So very quickly, right, we need to go through some of the basic fundamentals of electrochemistry, like what is electrolyte? Okay, so electrolyte is a compound. It has to be a compound, okay, with different ions make up of it. So normally it will be ionic compound, normally, okay, but not all the case, okay. In general, we use ionic compounds because in aqueous and molten state, the ions will be free to move around to act as mobile charge carriers. So the ions can move to the various electrode and have their redox processes, reactions taking place there. So electrolyte basically can conduct electricity due to the free moving ions that carry charges. Okay, so this will be the okay. Now, what is the difference between strong electrolyte versus weak electrolyte? So strong electrolyte, very similar to what you learn in strong versus weak acid, basically fully ionized or fully dissociates, okay, in molten or in aqueous solution. So these are the examples of strong electrolyte that we use in electrolysis. And there are some exceptional cases like covalent compounds that actually do ionize, like your acids, HCl or HNO3. Okay, they ionize in water completely to form ions, and which explain why acid can be strong electrolyte, especially for the strong acid. For weak acid or weak alkaline, they will act as weak electrolyte because they only partially ionize. So as long as they are free moving mobile charge carriers, then the substance can be considered an electrolyte. Whether it's strong or weak, it depends on the degree of dissociation. All right, if it's a complete ionization, then it will form a strong electrolyte. If it's an incomplete or partial ionization, then it will form a weak electrolyte. But there are also cases where we classify certain compounds as non-electrolyte because they didn't manage to ionize at all, like hydrocarbons, alkane, sugar, alcohol. Yeah, they cannot. Okay, so these exercises, right, are just a revision, so I will not go through it. You can just refer yourself, like you can cover the answer and try again. All right. Now, Electro potential, right? What is it? So let's recap the concept. So if you have a metal electrode that is immersed in an aqueous solution of a metal cation. So for example, you have, this is the electrolyte, and you have an electrode that is immersed in it. Okay. Let's say this is magnesium. And the solution used could be magnesium chloride solution. Okay. So if you immerse the magnesium rod into its aqueous solutions of magnesium chloride, for example, there are two possible processes taking place. So it is actually an equilibrium process. So we need to understand it's an equilibrium process. Okay, what are the two reactions taking place? So firstly, when the magnesium is deep into the solution, okay, magnesium is moderately reactive. Okay, so it will definitely lose electrons. Okay, so the electrons from magnesium atom will be lost and go into the solution with this half equation represented. So magnesium will be oxidized to form magnesium 2+ with the loss of 2 electrons, since magnesium is of 2+ charge in the ion or compound form. So what happens is that the electrons will just be left on the metal. The electrons don't go to the solution. Okay, it's the ions that go. So there will be ions here. The electrons will remain on the rod itself, the metal rod. So remember that. Okay, this is important. The electrons don't go into the solution. That's a wrong concept. So over time, right, on the surface of the magnesium, there will be a build-up or accumulation of electrons. And the metal inside the solution will be surrounded by a layer of positive ions. So what it means is that you have the metal, magnesium, the electrons are here on the surface or moving within the rod. Then surrounding the rod, you will have magnesium 2+ ions around it. Okay, that's what it means. At the same time, you will have the positive ions in the solution will also get reduced back to form the magnesium. So some ions will actually be deposited back in this reduction reaction. So this is reduction, while this is oxidation. All right. So there is two reactions taking place here, oxidation and reduction simultaneously. So when the rate of these two equations become equal, dynamic equilibrium is established. Dynamic because reactions ongoing. It's not a static equilibrium, it's dynamic. There is still reaction proceeding. Okay, so you combine these two equations, you change the arrow to a reversible sign. Okay, so at equilibrium, there will be a constant negative charge on the metal and a constant number of ions present in the solution around the metal. Negative charge because of the electrons. Okay, now over time, right, constant doesn't mean the number of electrons and the number of positive ions is the same. Right? Constant means no further change. So the number may not be the same, and it will not be the same because the mole ratio is different. Okay, but constant means no further change in the number because equilibrium is already achieved. Okay, so that's the concept. So over time, you will expect the metal become more and more negative charge until there's no further change because of the electrons that's accumulated or built up. And the solution surrounding the metal rod will become more and more positive charge because of the accumulation of metal ions that are positively charged. So there is a separation of charge across the metal solution interface. So you will see that, okay, so this thing, this metal rod will be somehow negative. Okay, surrounding the rod, which is the solution, will be positive. Okay, so there will become a separation of charge across the metal solution interface. That is how potential difference is generated. Okay, that is the understanding of, oh, there is a potential difference. Potential difference arises, occurs when there is a difference in the potential. Okay, there's a difference in potential because the amount of charge is different. All right, there is a difference between positive and negative charge. Okay, now this configuration of electrode and the solution is called half cell. Okay, of course, there are other types of half cell like gas ion system or ion system. All right. Now, how do we measure electrode potential? The so-called electrode potential, which is the absolute potential, cannot be measured directly, just like your enthalpy. Cannot. You need to be very, very clear on this. Okay. So we always calculate the difference in potential. Okay. I'm not saying potential is not a value. It is a value. It is valid. But in experiment, you cannot determine it. So what it means here is E cannot be measured directly in experiment. Okay. Just like enthalpy. Enthalpy cannot be measured directly. You need to find the change in enthalpy by taking the difference in temperature times the mass times the specific heat capacity. Yeah, because it is a theoretical concept that cannot have any way to measure it. There's no instrument to measure it. Just like in your lab for physics, you have voltmeter. The voltmeter can only measure potential difference, but not potential. Okay, same thing. So it cannot be measured directly. So this is only a half cell, which means you need another electrode, another half cell to complete the cell. Okay, and the other electrode will introduce its own potential. So that will result in a potential difference. Okay, this one will only tell you the potential. Okay, but when you connect it to another half cell, there will be a potential difference. All right. Okay. Meaning this one, I cannot measure it. I need to connect to another half cell and put a voltmeter in between. All right. So these are the conditions that will affect or causes changes in electrode potential: temperature, concentration of the ions, or partial pressure of the gas. So the measurement of standard, standard electrode potential depends on, or should I say requires two things. Number one, the standard electrode, which we are using the standard hydrogen electrode, okay, as well as carry out this in standard conditions. So let us talk about what is standard hydrogen electrode, a quick refresher. So a standard standard hydrogen electrode known as the SHE. This is not the Taiwanese girl band, SHE. Okay, yeah. A lot of students in the past. Okay, during my time when I was learning this in JC. Okay, I only learned this in JC 2001. or at that time, it's a year where you have the 911, yeah. And during that time, yeah, this girl band is super popular. So everybody is talking about it. Yeah, this one. Yeah, but now they are not that popular lah. So you may not be aware. It's not your generation popular band. Your generation is Blackpink. Yeah. Yeah. I mean, many of students are going for their concert actually. The tickets is 300, 400 plus. My student all bought it. Yeah. But this one at that time is the Blackpink that time. Yeah. Whereas people will save up money to go for concert and go for the autograph. But anyway, that's sidetrack. So SHE, standard hydrogen electrode, consists of a platinum electrode coated with finely divided platinum. Okay, so we call it platinum black. Okay, that is the name given to a finely divided platinum. All right, then so the electrode is a platinum because it's inert. Yeah, inert. You learned that before, right? Yeah. But they don't really use it often because it's not cheap compared to your graphite. Yeah. But graphite is more unreliable because it will need to be replaced more frequently because it will react with oxygen to form CO2 and then the mass will decrease gradually over time. So you need to replace it. Okay, the concentration used is the standard concentration of hydrogen ion of 1 mole per dm cube. So must make sure that it's 1 mole per dm cube. So this must be 1 mole per dm cube. Okay, no argument. The hydrogen gas is bubbled into with a pressure of 1 bar. Okay, the temperature is set at 25 degrees Celsius or 298 Kelvin, which is the room temperature. Okay, in the past. Now the room temperature has been adjusted to 20. However, we still keep this because if you're going to change the temperature, then the reading will differ. Okay, so platinum is inert. So because it's inert is used, it will not affect the experiment result. It will not be participating in the redox processes occurring here. So this is just the half cell for the hydrogen electrode and it's standard because of all these standard conditions. So the electrode itself will allow the hydrogen to be absorbed. Is absorbed, not absorbed, meaning it is only sticking on the surface. Okay. Not going into the electrode. Okay. Very, very clear about that. Something like this. Okay. If you want to imagine it. Okay. So when the hydrogen is absorbed, okay, it loses electron to form H plus. But of course, at the same time, simultaneously, the H plus in the electrolyte will also get reduced. So there's this equilibrium, this dynamic equilibrium occurring. Okay. And the potential developed will be arbitrarily assigned. Arbitrary means, yeah, you just assign it so that everything else that's connected to it will be the standard electro potential. Okay. So the black coating, which consists of the finely divided platinum, is to increase the surface area. So type of mistakes. Okay, that will increase the surface area of the electrode to establish the equilibrium more quickly. Okay. They also use other reference electrode. So in case they ask you, you'll be prepared for it. But if you use other standard electrode, then it will not be a 0 volt. They will have they will use other voltages. So this is just a recap of the standard conditions. Just take note of that. And the symbol represents standard conditions and it's always written as a superscript, this thing. Okay, so just be aware of that. Okay, a quick exercise. Now, so if you set up this electrode, hydrogen electrode, what will be changed to make this a standard hydrogen electrode? So you have to examine the diagram to see what is wrong with it. I think it's the temperature. Yeah, can you see that? No need to quite fast. I look at it, I find it very fishy already. So they actually use the wrong temperature and regard it as a standard. So that is the only change. No need to think so much. It's memory work. You can see how easy past the paper is. This time, 1995, 6, 7, 8, 9, 2000. Anything before 2001, the paper for both O and A level are super easy. There is not much thinking question. There's no long database question. Okay, the question is something like this, straightforward. It depends on whether you study or not. Yeah, a lot of people get A. Yeah, very easy. A1. Yeah, very easy. Yeah, and there's only some thinking question only. Yeah, and the answer all short and sweet for chemistry. Yeah. You know that even for A-level chem, right, my time, right, they don't even teach so much things, you know, in organic chem. Like the mechanism you learn, right? There's only 3 mechanisms we learn only. 1, free radical substitution. 2, electrophilic addition of alkene. 3, electrophilic substitution of benzene. The end. The rest just remember reagent conditions. So you don't even know, we don't even learn what is SN1, SN2, we don't know. We don't even know, of course, we need to know all the carbonyl compounds, but we do not need to learn so much content. Yeah. And yet the questions are more or less very straightforward. It's something like this. The OO paper. Yeah. Because right, before that year, right, I think Singapore is still using the UK version. So we are doing the same paper as the UK people. After that, they changed for both O and A level. They decided that it's too simple for Singaporean. So they have Singaporean to set the paper instead. So we take a different paper from people in Brunei, UK, and other countries, other Commonwealth countries. Yeah. So they are still doing this standard of paper. Yeah. Not fair. Very not fair. Yeah. That's why they are very impressed. Other countries are very impressed with the standard of science and math in Singapore. It's really, they find it really very high. Yeah, our students came in, when we go overseas to study, the Singaporean students are the top students. Yeah, because they have been trained to think critically. So they can handle very difficult questions in the university. They outsmart the foreigner, the local there. Yeah. It's just like foreigner come to Singapore, they outsmart us in our uni lah. It's the same thing. It's always like that. Okay, so this is the diagram that represents electrode at 298 Kelvin. So they're asking what should be the condition on the surface of the platinum and the concentration when taking the measurement. Okay, so the thing is, many people might choose B or D. Okay, first of all, the platinum electrode, right, should not be polished. The better word is platinized. Platinized means you coat with finely divided platinum, meaning the electrode itself, right, you still put fine platinum particles on it to increase surface area. Okay. Then many people might choose 0.5 is because because they thought that, oh, everything is 1 mole per dm². But we are talking about a dibasic acid here. Yeah, that's the tricky part. So if you're a dibasic acid, right? Okay, every 1 mole of molecule, so every 1 mole of acid molecule, okay, dissociates to form 2 moles of hydrogen ions. So if the concentration is 0.5, the concentration of hydrogen ions will be 1. Okay? Yeah, be careful of that. So that example earlier on is for monobasic acid. But if you are using a dibasic acid, right, we have to be careful the concentration of the acid used. It will be 0.5. Okay? Now, what is standard electrode potential? So now we're going to connect this standard hydrogen electrode, SHE, to your measured cell. Okay, the cell you want to investigate. Okay, so if the half cell is connected to the hydrogen electrode, which is also a half cell, the resultant cell has a potential difference called electromotive force. Okay, this is something that you learn in physics. Okay, so because we are talking about electrochemical cell here, and we are still not on electrolysis yet. Okay, we are still not on electrolysis. We are still talking about electrochemical cell. So the term used is electromotive force, which is the amount of potential difference somehow generated. You know what I mean? Potential difference in physics defined as the amount of energy per unit charge. So it's like generating energy. So potential difference is equals to the amount of energy generated per unit charge by the source. So when you say EMF, right, it is like energy. Okay. So when there's a difference in potential, current flow or charge flow, then there will be EMF generated in the form of energy per unit charge. So if EMF is measured under standard condition, its value is known as the standard electrode potential. So standard electrode potential of the half cell is the electromotive force measured at 298 Kelvin, 25 degrees Celsius, between your measured half cell and the standard hydrogen electrode. And this is the concentration and the gaseous species pressure at 1 bar. Okay, so instead of just like, you know, electrode potential, so in your data booklet, okay, they will refer to it as reduction potential or redox potential. It means the same thing. Okay. So these are the common half cells. We have metal ion, gas ion, and ion. Okay, gas ion is similar to what you see in SHE. Okay, metal ion is the earlier example of magnesium. So the other one is the ion where you have 2 different types of ion. For example, Fe3 plus and Fe2 plus. And normally we will choose transition metal because they can transit between ions. So each system primarily contains the same element in different oxidation state. So in the absence of a metal in the half cell, okay, we will just use platinum as the inner electrode. Okay, one more question here. This is the standard electrode potential or redox potential. So they were asking which cell is used to determine this standard value. So you just need to check this against, so this is, so if you want to check this, right, you need to compare against SHE and not compare with the other ion, okay? Because they are using the word standard. So it must be connected to SHE. So the one that is talking about SHE will be D. Okay? So you must talk about platinum electrode, not iron electrode, platinum electrode in a solution that contains 1 mole per dm³ of Fe3 plus and 1 mole of Fe2 plus against a standard hydrogen electrode. So for this one, you need to connect to a SHE. Okay. And the electrode here should be platinum. Okay. Because this is obviously the ion electrochemical cell. Okay, so you already have Fe2 plus, Fe3 plus. Yeah. If not, if you use iron electrode, it will affect the reading. It will not be accurate. Okay, next part is the measurements of the standard electrode potential. So how to do, what are the steps involved? So we're going to talk about salt bridge very soon. So first of all, you set up the half cell and the SHE next to each other, okay, as shown in the diagram below, and ensure that their concentration is standard at 1 mole per dm cube, standard temperature, standard pressure if there's any gas. Then you connect the two solutions in the two half cell with a salt bridge. So the salt bridge normally contains saturated potassium nitrate solution. So basically the salt bridge, right, will complete the circuit because the salt bridge itself has free moving ions, okay, that will move, that will still allow a continual flow of charges from one to another. So if you break that, you remove the salt bridge, right, okay, then it will not be a complete circuit. It will just be here to here and that's it. Okay, there will be no continuous flow. Okay. So you have a voltmeter in between the two half cells. You measure the PD, okay, and then you take the reading as the EMF of these cells. Okay, so the first reading shown on the voltmeter, the moment the two half cells are connected, is the actual EMF. Okay, what happened is that if current is allowed to flow in a closed circuit, there will be chemical reactions taking place. And over time, right, the concentration will start to fall or decrease. So this is the reason why once you connect, you should immediately take the reading because subsequent voltage reading will be smaller. Yeah, just like when you set up a circuit, right? Over time, right, you realize that how come the voltmeter is reading a smaller and smaller value? Because there is already some depreciation of voltage along the way. There is some loss of power due to resistance, due to current flow that will affect the voltage. Okay, so the reading on the voltmeter will eventually drop to 0 when the cell goes flat. Just like your battery cannot last forever, the voltage will keep on decrease. Okay, until it reaches 0, then you cannot use it anymore. You have to replace the battery. All right. So when the voltmeter reading drops to 0, it means the system reached equilibrium and there is no more potential difference. All right. So this is an example of experiment set up between copper. It's a metal ion system here. Metal ion system. Metal and ion system. All right. So what happened is that, hey, you have the anode here, okay, and the cathode. Okay. So the electrons will flow from the hydrogen half cell towards the copper half cell. Why? Why towards the copper? Because if you recall, copper is below hydrogen in the reactivity series. So copper is more likely to undergo reduction compared to hydrogen actually. So in this case, right, because copper 2 plus to copper is more easily reduced compared to hydrogen, which means that you have a positive standard electrode potential, implying reduction is favored. If you have a negative electrode potential, it means oxidation favored. Okay. Now, at the standard conditions, the reading on the voltmeter will give the standard electrode potential. So if you refer to your data booklet, okay, that will be all the standard electrode potential. Okay, I do not know whether you have the data booklet. Data booklet is the A level, it's in the A level syllabus. Okay, let me take out to show you where you get the readings from in the booklet. Okay. So the A-level chem syllabus list is the longest because they have the data booklet right at the back. Okay. For Olympiad, they will provide the data, don't worry. if such question is ever tested. So this is the longest document ever in the A-level syllabus because of the data booklet. Yes. Okay. So the data booklet of the A-level is very comprehensive. So on the first page, it already show you all the constants. And the next pages will be talking about IE. They also have bond energy, but not all. So sometimes they may just require you to refer to the data booklet. And then, this is the one. This is the standard redox potential at standard conditions, obviously. So the copper is here. You see that? Be careful, we are talking about copper 2+. So this copper 2+ reduced to copper is 0.34 volts standard redox potential. All right, okay? Yeah, so this is how you get the data. Now, so remember to code the sign because we need to indicate whether it's a positive or a negative. It's very important. Okay, so as mentioned, the salt bridge complete the circuit where ions can flow to maintain charge neutrality. So this salt bridge, right, will also prevent so the ions near the electrode will not just accumulate, that it will flow towards the salt bridge in a way. You don't want it to accumulate too much. All right. Now, the voltmeter gives an indication on the direction. So if you see a positive value on the voltmeter, it shows that electrons flowing from the hydrogen electrode towards the copper. Okay, so positive means, okay, electrons flow from hydrogen to copper electrode. Negative means the other way around. Electrons flow from, sorry, I should just put metal. From the metal to the hydrogen electrode. Okay. So that is the meaning of it. Now, so let's look at another example. We have zinc as the more reactive metal. So in this case, right, the electron will flow the other way towards the hydrogen electrode. And if you refer to the data booklet with all the electrode potential values, okay, zinc, okay, let me teach you how to read this. Very easy. It is in alphabetical order in terms of the chemical symbol, not in terms of the name. Like silver, Ag comes first. Okay, and zinc is capital Z. So it is the last one. Okay, and this is how you read so that you can quickly get the value. Okay. So the voltmeter readings will give an indication of direction of electron flow. You see a negative value here. Okay, negative value means that the electron is flowing from the zinc to the hydrogen half cell. All right, so actually it should not say, should not say electrode. From the metal electrode is okay. From the metal half cell better. Yeah, clearer. Because the electrode in the hydrogen electrode, the hydrogen electrode is actually the platinum. So should say half cell. Yeah, better. Okay. Yeah. Now, so it means that hydrogen ion is more easily reduced. So you see a negative sign means it's not easy to reduce zinc 2+. Now, another example, you have a gas ion system, fluorine. All right, so in this case, fluorine actually get reduced very easily because group 17. right? So and fluorine is super reactive. We all know that it's the most reactive non-metal in the periodic table. So the standard electro potential, I call it E0, is super high, plus 2.87. Okay, so electrons will flow from the platinum electrode to the platinum electrode with the fluorine half cell. All right. So make sure you can sketch this, at least know how to recognize this. And we'll need to draw at A level. Okay, next one is ion-ion system. Another example, MnO4 minus and Mn2 plus. So in this case, again, this is because MnO4 minus is a very strong OA. Okay. It's a very strong oxidizing agent. So because it's a strong oxidizing agent, it will be reduced very easily. So strong oxidizing agent reduces itself easily. Okay, so the electro potential is positive. All right. So by convention, right, we represent redox potentials as reduction processes. Since we call it redox potential, normally we just represent reduction. So in your data booklet, as observed just now, everything here is in terms of reduction, all of it. Okay, so if you want to write the oxidation equation, just flip the equation to the other way. All right. So you can also infer that fluorine is the strongest oxidizing agent because it has the highest standard electro potential, while lithium is the strongest reducing agent. Okay, lithium here, you see, minus 3.04, so it's the strongest reducing agent because it oxidizes itself more easily. Now, so the magnitude of the standard electro potential is a measure of the tendency of reduction. The keyword reduction. How easily reduction takes place. So the more positive the value, the more likely the reduction will occur. Okay. In other words, the more negative the value, the position of equilibrium is more to the left where oxidation is favored. So looking at the E0 value, the redox potential value, will actually tell you the position of equilibrium. If you have a more positive E0 value, your position of equilibrium is towards the right. So it is favoring the reduction process. So here, favor reduction. Okay, when you have a positive value. If you have a negative value, it favors oxidation, where equilibrium lies to the left. Here we are referring to the half equation that shows the reduction, not the oxidation. Okay, so the more positive the E0 value, the forward reaction is favored, more likely to have reduction, higher tendency to gain electrons, stronger oxidizing agent. More negative, backward reaction favored, more likely oxidation, higher tendency to lose electron, and the reducing agent is stronger. So whenever direction the half reaction is reversed, remember, you must reverse the sign. So if you ever try to reverse the direction, do bear in mind that you also need to reverse the sign. The value itself, not the sign, will not be affected, even if you flip. Okay, but if you need to multiply, this is very important. So I'm going to star this. Many students actually not aware of this. So they they confuse this with enthalpy. Enthalpy is different, huh? For enthalpy, right, if you multiply by the coefficient, right, your enthalpy change also multiply, correct? That is true for enthalpy in the topic of energetics. But for electrochem, right, please bear in mind, even you multiply by 22,000 times the coefficient, there is no change in the standard redox potential. No change. Okay, no change. All right, so even if you want to times 2, times 3, it will still remain the same value for the E naught. All right, yeah, same. If you flip, of course, it becomes a different sign, but the value is the same. Okay, so doubling the coefficient do not double the E naught value, as the standard electropotential is actually the ratio of energy to charge. So when we change the coefficient, yes, the amount increases, but the energy also increase proportionally. Yes, because when you increase the amount, the energy and charge increases proportionally. So the ratio is the same. So electropotential is a ratio. It is similar to the concept of density. So the density will be constant at a constant temperature. So you can try to increase the volume. Okay. It won't change the density. Okay, if you still use the same mass lah. All right. Sorry. If you increase the amount, it will not. Meaning, like for the concept of density, right? It's like you have one small cube. Okay, you add a similar cube and mash them together, right? The density is still the same. Okay. So the overall density remain constant. That's what I mean, sorry. Okay, meaning that you multiply the amount, you will not change. Of course, if you change the volume, it will change lah. But I'm saying if you just add on to it, it will not change. Okay. Or you remove part of it, it will not change the density. Same thing. Now, for redox series, I think I already go through the standard electropotential, how you can extract the value from the data booklet on the redox potentials. Yeah, and they are arranged in alphabetical order and also in order of decreasing E naught value. No, I think not. Oh, it's a bit mixed up. Yeah, not really for this book. Yeah, not really. Yeah, no. But they are more like alphabetical order. So either they, do they have it there? Oh, here, sorry, next page. So there's one reading, right? One table is alphabetical order. The other order is in terms of electropotential. So they start with the most, the strongest oxidizing agent first. Then they go down the list. You see? So this is not in alphabetical order. Okay, so they are going down the list here. Okay, can? Yeah. But this is just a selection only. They are not showing everything. So if you want the specific one, the alphabetical order will be the whole list that they will test you. So for the series, in order of decreasing E naught value, the species on the left-hand side at the top are the strong oxidizing agent. Those at the bottom are strong reducing agent. Okay, strong oxidizing agent because they reduce itself easily based on the E naught value. And strong reducing agent means they oxidize itself easily. Therefore, they can reduce other substance when we react with it. Now, there is a very close relationship between E naught and reactivity series of metals. Now you know. Okay, so I think in your syllabus, right, you only remember the reactivity series, but actually the reactivity series is related to the E naught value. Yeah. but they only introduce it at higher level. So this is the true story. Okay, so from silver to lithium, the reactivity increases. Yes, correct. Good one are the most reactive metals, right? Then the E0 become more negative. Yes, more reactive means loses electron more easily, so they are stronger, reducing agent themselves, so they oxidize easily. Yes, yeah, all this. Okay. So these are just some exercise to make reference to very quickly, like what is the strongest oxidizing agent? Fluorine. Then based on page 11 to 12, which is this list, just based on this list, according to the question, it's potassium. But we know that it is not potassium, right? It's actually lithium, but because the question says based on that 2 pages, you see, yeah. Okay. Then the standard electro potential, just fill in the blanks. Very straightforward. I won't go through this. Just remember the sign, okay? Then halogen, the Cl2 is definitely a stronger oxidizing agent based on the E0 value, because this is 1.36. This one is 1.07. So Cl2 is a stronger oxidizing agent. As for the metals, zinc is a stronger reducing agent because the E0 value is more negative. Okay. Okay. Then after that, these are some more questions, basic questions lah. Silver plus higher tendency to gain electrons, correct or not correct? So correct lah, because it is less reactive, right? Silver. And you look at the E0 value, this is 0.8. Then hydrogen is 0. So 0.8 positive means more likely to reduce, more likely to gain electrons. Magnesium, higher tendency, yes, correct. Magnesium, aluminum, magnesium more reactive, right? And look at the E0 value, magnesium to silver. Magnesium is more negative, so more likely to lose electron, correct? Fluorine, higher tendency to gain electrons compared to chlorine. Yeah, and so on and so forth. Okay, this one you can just read yourself. Be careful, look at what are they talking about. Is it, so here and here is the ions. So you have to look at it in the correct way. So chloride, for example, the last one, to form chlorine. So chloride to chlorine is not very likely, it's negative, right? So it's more likely to lose electrons, not gain. But actually, the way they put it is a bit weird. It should actually be, lose electrons, yeah, correct, it's correct. This way better, lost electrons than fluorine. Or because it's more negative, yeah, so it's easier this way. So the opposite will be, yeah, difficult lah. So difficult for F minus, correct, it's correct. F minus difficult to form back F2. Yeah. Just don't get confused. All right. What is losing, what is gain? Now, so the first part of the electrochem is basically on the electrochemical cell. Okay, not on electrolysis yet. So okay, so this is just some of the terms they use, like voltaic cell, electrochemical cell, it's the same thing. So when a streak of zinc foil is dipped into copper-2 sulfate, okay, now you think about, okay, I'm going to put the metal in solution that is of a different metal. Okay, what will happen? Of course, we know that zinc is more reactive, it will dissolve, and copper-2 plus will get displaced, right, and reduced to form copper. So a brown deposit or reddish brown is formed on the zinc foil, and we understand that displacement reactions are exothermic. This one we learned that before. So do remember the list of reactions that are exothermic and endothermic. Okay, very important. Okay. So you form zinc 2 plus and copper. So in these reactions, the electrons are basically moving from the zinc atoms to the copper 2 plus ions via the metal solution interface. So by simply extending the road of electron travel, the chemical energy of this reaction can be converted to electrical. This is how we actually generate energy. from chemical reactions. Okay, that's how it was done. So this is what we call the zinc half cell, copper half cell. Together we call it electrochemical or voltage cell. For zinc copper in particular, because it's very commonly used, so we call it Daniell cell. Yeah, Daniell cell. The Daniell is double L, not single L. Okay. So electrochemical cell is also batteries. So that's how your battery works. Yeah, your battery works in this way. Like some battery work on Daniell cell. So if you just have this, right, it will not be useful because whatever chemical energy, right, will be converted to heat and not used. But if you could use the chemical energy to electrical energy, okay, then it will be useful. What will happen is that you can actually store. So this battery can become, you know, a source of energy, actually. Yeah. So this is the Daniell cell in with more elaboration. You have the anode, cathode, obviously. Then you have the zinc. The zinc is the anode because the zinc is a more reactive metal with a more negative standard electrode. So I'm going to change all the terms your teacher use at O level and RP level, where they actually say this is more reactive than this, therefore it's like that, right? Change. I think you learn simple cell already, but I would like to emphasize more on the redox potential. That is actually more correct and precise. Okay, instead of saying reactivity. All right, that is not wrong but not completed. So zinc is of the zinc half cell have a E0 that is more negative, so it will be the anode. All right, copper is more positive, so it will be the cathode. All right, so you have to compare the E0 value to assign the anode and cathode correctly. So the E0 of zinc, this is how you write it. So E0 of zinc 2 plus, zinc half cell is more negative. Correct, more negative. So zinc more easily oxidized. Yeah, this is the correct, complete understanding. Meaning zinc has a higher tendency to lose electrons, so lose electron more easily. Okay, or we can say that the other way around, copper 2 plus, copper half cell is more positive, copper 2 plus more easily reduced, copper 2 plus higher tendency to gain electrons. So what happened at the anode is you have the zinc losing 2 electrons because it must form a zinc 2 plus charge. Okay, reason wise, it's something to do with the configuration that it can only form this. Okay, yeah. The next chapter that I'll be doing on transition metal complex will share about why only zinc 2 plus. Unlike copper, can be copper plus and copper 2 plus. Okay, it has something to do with the SPDF, the d orbitals. Now, the copper 2 plus in the solution near the copper metal will take up the electrons, yeah, and reduce to copper metal reduction. So this is the overall redox reaction. So this is so-called the Daniell cell. Of course, you have the salt bridge in between. So the electron leaves the zinc electrode and travel via the connecting wire. So the electron only flow on the metal surface and the wire, not in the solution. So remember, we are talking about electron flow, not the conventional current you learn in physics. Okay? Because when the scientists discovered electricity, atomic structure was not developed yet. So they do not know that there are electrons. But actually, it is the electrons that contribute to electricity. Okay? But after the discovery, right, the physics people won't want to change. They say, no, we are not changing because it won't affect the operation. So they say that since it won't affect, why should we change? Yeah. So they're quite stubborn. Physics people are very stubborn. They insist they are the best, which is true to some extent. Yeah, physics people are smarter. Okay. If not, we don't have most of the famous scientists are physics people, right? Yeah. Chemistry is like a lower level lah. Like they regard lah. So they say that no, we just call it convention current, but the chemist people, right, will still keep it as electron flow lah. So that's a bit of conflict between them, a bit lah. Okay. So and now you know why you have 3 different science teachers. Sometimes their ideas will conflict in different ways. Yeah. Like for example, I give you one example. Bio teacher would say that you can say lower the activation energy, no big deal. But the chemistry people cannot accept it. You must say alternative power lower activation energy, for example. So different discipline have different experts which insist their own way. Yeah, so you have to be mindful of that. Okay, Ken? Yeah. But since you are doing chemistry, you listen to me. Okay, no lah. Okay, so just for chemistry, you just regard electron flow instead of conventional current. Don't confuse with the physics part. The salt bridge as well, complete the circuit, nothing much to say about it. It just ensure charge neutrality, prevent accumulation of charges, blah, blah, blah. Okay, then I think these are just the convention I taught you before, an ox red cat, right? So oxidation, anode, reduction, cathode. It also apply for the electrolysis later on. Okay, so I'll skip this. Of course, you have more positive E naught value, more readily or easily reduction occurs. Okay. Okay, so the salt bridge, right? Let us elaborate a bit more. What is it? So for the electrochemical cell, the electrons flow in the external circuit from the anode to the cathode. The 2 half cells are connected internally by a salt bridge. Okay, we call it a U-tube, okay, that contains an electrolytic solution. So KNO3, just one of the example. You can have other salts, okay, where ions do not react with other ions in the cell of electrode. So this is just simply KNO3, all right? So what happens is that the electrolyte conduct electricity, but does not allow mixing. So you have the salt bridge here, correct? So what happens is that you might need to bear that in mind, right? This salt bridge, right, will only allow it allows the continuation, the electricity to be conducted lah. But the ions here remains here. The ions here remains here. That's what it means to do. It doesn't allow them to, you know, you may ask this question, how come you just don't mix them together? So complicated, the salt bridge, because you need the salt bridge to separate the ions from each other. You don't want them to mix with each other, okay? But you still want to ensure that there is flow of electricity to complete the series circuit, correct? So in the Daniell cell, as zinc 2 plus continue to be produced, the zinc ions build up a positive charge, okay? So what happens is that more and more zinc 2 plus form due to oxidation of zinc. You have accumulation of zinc 2 plus. Similarly, around the copper electrode here, more and more CO2 plus is reduced. You have less and less CO2 plus around here. And it becomes increasing negative relatively because the sulfate in the copper 2 sulfate remains, they didn't get discharged. So the sulfate ion become not more, but relative more. It doesn't increase in the actual amount, but in terms of the relative amount, it get more, okay? So you have an excess negative charge here and excess positive charge here, okay? So the ions in the salt bridge will migrate. So what happened is that the ions in the salt bridge will come out to neutralize the charges. That's to prevent accumulation of the charges. You get what I mean here? So the NO3 minus, for example, because there is accumulation of positive charge of zinc 2 plus. So the zinc 2 plus too much already, right? So the nitrate come out and neutralize the zinc. Neutralize the charges here. Then the K plus will come out to neutralize the charges. Okay, it helps to remove the excess negative charge here. Okay. So the salt bridge, right, provide positive ions and enter the copper 2 plus solutions, and the negative ions enter the zinc 2 plus solution. So what is flowing is the ions of the salt bridge, the KNO3. Okay, so the ions flow, and when the ions flow, right, because it will prevent the ions from coming here. So the ions here cannot go in. You get what I mean? But you still have the mobile charge carriers there. Yeah, so like it will still continue the flow of charges, but it will be different charges lah. You get what I mean? Yeah. You don't mix the charges on both sides, but still allow movement of ions, but different ions lah. Okay. Now is standard cell potential. Okay, so if any question, you can stop me now before I move on. Okay, can? Okay, can? It's okay, you can talk, don't worry. It's okay. Okay, now, I mean, if it's something you want me to clarify, I can pause and go. Don't worry. It's no need to finish this today. It's okay. I'm not rushing. Yeah. It's best that you understand the concept. That's more important, and apply to the question. Okay. So I try to cover as much as I can. I try. Okay, so Enoch cell is the potential difference between two half cell under standard condition. It's a repeat of what we have covered. Okay, not a repeat. Okay, just now it's just potential difference, but if you combine the two half cell together and you measure the PD, that will be called Enoch cell. It will be standard if it's carried out standard conditions only. So it's a measure of EMF. This is what you learn in physics, EMF, which is the Enoch cell. So it is actually the energy to pump the electrons, somehow like that. Now, they don't call it energy because it's actually energy per unit charge. So they just call it electromotive force. So the standard potential of electrochemical cell can be calculated by this. Enoch cell equals to Enoch cathode minus Enoch anode, or Enoch reduction minus Enoch oxidation, same. Try not to change the sign of Enoch given in the data booklet. I mean, my advice is just use the formula directly, which is simpler and less confusing when you need to calculate the Enoch cell. This is very important. It will be required. So Enoch cathode is the reduction potential of the half cell undergoing reduction. Enoch anode is the reduction potential of half cell undergoing oxidation. Okay, fine. So for the Daniel cell earlier on, let's do an example. Zinc 2 plus oxidized to zinc minus 0.76. Copper 2 plus reduced to copper plus 0.34. So this is the reduction. This is the oxidation. So immediately you recognize this as the cathode. Reduction, because it's more positive. So reduction is the more positive electrode potential. This one, anode minus 0.76, more negative. Okay, more positive, more negative. So you just add them together, you get plus 1.10 volt. So plus 0.34. But this is negative, so you need to take negative, negative, become positive. So the Enoch cell is plus 1.10 volt. Just use this formula all the time. Don't turn the sign around. Just add them minus, minus. Okay, easier. Just use this formula and just plug it in. Okay. Always put the cathode first, followed by the anode. The order very important. If not, you will get a value wrong. Okay. Now, so for this exercise, you are given voltaic cell made up of the following half cell. Write equations and the overall cell reaction. Calculate and draw the labeled diagram for each cell. So first one, you have Cl2 and Fe3+. So identify the more positive one, meaning if both are positive, right, look at the one with a greater magnitude. It will be Cl2. So after that, use your formula. 1.36 minus 0.77 is positive, so just minus, so it's 0.59. Remember the sign? And this is the overall equation. I will not go through. It's very straightforward. Should be able to do it yourself now. How to balance two redox reaction to form one, okay? No need to go through. And then after that, this is the half. They want to draw the half cell. Because you know why? Because one of them is a gas, Cl2 ma. So it's something like the hydrogen electrode, SHE. So you must draw something like that. Cl2 indicate the standard condition. 1 bar gas must indicate the pressure, indicate the concentration. Fe2 plus, Fe3 plus is ions cell. So must indicate both. Remember, it's platinum, connect, electron flow from here to the other side, because this is more likely to undergo oxidation based on the E0 value. Okay, they will write for the other one, same thing, just copy and paste from data booklet. This will be provided like the value. Just pick the correct value. You pick the wrong one, that's it. All right, and then this is more positive, so this reduction, that one oxidation, so just say 1.33 minus 0.17. That's it. Okay. Now, so these are for standard condition. What if I change it to non-standard condition? How will that change the calculation? Okay. So if you have non-standard condition, like this half cell, let's look at the same scenario, same example. So if that happen, all right. Okay. If the let's say if you, okay, depend on what you are changing, okay? So if you are going to increase the concentration of Fe3+, you want to make this beyond 1 mole per dm cube. So you have to consider Le-Chatelier principle, how the equilibrium shift. So with increased concentration of Fe3+, the position of equilibrium will shift to the right. When it shifts to the right, means that reduction occurs more readily. It means your E0 value will increase. On the other hand, if you decrease the concentration of Fe3+, that is to be less than your standard concentration, then your position of equilibrium based on Le-Chatelier principle will shift to the left to have a less positive E0, E value. So it will be less than that. Okay, so just bear that in mind. Your E cell will not be the same as E0 cell if the conditions are non-standard. Okay, for example, this exercise, right? You have this Botic cell of these two half cell, copper and iron. So you calculate the E0 cell, E0, so again, more likely this one, so 0.77 minus 0.34, easy. So this one will be the cathode. And this will be the anode. So you assign first so that you can plug into the equation correctly, this one. Then, if you make changes, so what will be the effect? So you are not required to calculate, but you only need to know the effect, whether it becomes greater or smaller, that's it only, okay? Of course, if you want to calculate, then they have to provide that, then actually there's a way lah, okay? But it's not, yeah, it's not covered. But if you want, I can go and find out for you, like later on, like because no time already, I will check out how to actually calculate. There's a way actually can calculate one, yeah. So you have to add something. Okay, so this one, right? If you add water to the copper 2+ copper half cell, the equilibrium position will shift to the right because you add water. Okay. So the E cell will be greater than E0 cell. Why? Because adding water, right, it shifts to the side with more ions. So you have 2 ions here versus 3 ions here. So why does it shift to the right? It's because, right, on adding water, the position of equilibrium shifts to the left for copper 2+ and copper. but there's no change in position of equilibrium for the Fe3+, Fe2+. So you add more water, right? It favor the ion, so it moves to the side with more ions. That's it. Yeah, because the ion dissolve in it. Yeah, because we add more water, they dissolve more, something like that. Okay. Then for NaOH, right? Because when you add NaOH, right, it forms CuOH2. It's a blue precipitate. So it will shift to the right also, because you add more OH minus, it will remove the Cu2+. So what happened is that we add MOH. So the concentration of, because it forms the precipitate of CuOH2, the concentration of Cu2+ will drop. Okay, so this one is a PPT. So formation of PPT will cause the concentration of the ion to decrease. So it shifts equilibrium position to the right. So your E cell will be greater than the standard one. If you use a smaller piece of copper, no effect. Doesn't matter. Adding water to the Fe3+, Fe2+, no effect because it's the same mole. But copper, yes, because copper is different. They are one solid, one Cu2+. Yeah. But for the Fe3+, because same number, so no. Then here is because one more mole. Okay. Relatively. If you add some FeCl2, then it will shift to the left because you increase the concentration of Fe2+. So it shift equilibrium to the left. All right. So it's a recap of Le Chatelier principle. Now, if you have Cr2O7, Cr3+, addition of water will also shift to the left because there are more ions on the left. Okay. Then the addition, this one I think I won't go through. I'll talk about that already. Okay, now the next part is using the E0 cell. How do we predict spontaneity of a redox reaction? How do we know that, hey, okay, whether this reaction is spontaneous or not? We do not say whether it will occur, but spontaneous. That's the correct term. Whether it will just occur by itself easily without any much of the external influence. So if the E0 cell is greater than 0, we can say the reaction is thermodynamically feasible and spontaneous. But it is not related to kinetic. Can I say that? Yeah, not related to kinetic feasibility. Remember that. Okay, thermodynamically feasible or energetically feasible is not the same as kinetic. So if this reaction got very high EA, I'm so sorry, it cannot occur also. Okay, but whatever we are discussing is based on E0 only, which is thermodynamically feasibility. It's not kinetic. Okay. For example, let's say if you look at, let's say you had an enthalpy. Remember the graphite to diamond? The enthalpy change may be very small, but because the EA is so high, right, kinetically not possible. All right. Okay, if E0 cell equal to 0, reaction is equilibrium. If E0 cell less than 0, not thermodynamically feasible, not spontaneous. If you set up, you will not form the reaction, no reaction. So what are the steps involved? Number one, identify the species, what is reduced, what is oxidized, write the two relevant half equation and E0 value, identify the cathode and the anode, calculate the cell, the electro potential cell. If it's more than 0, spontaneous. Less than 0, not spontaneous. Okay, let's try. So you have these reactions. All right, same thing, the Daniel cell again. So copper 2+ and zinc 2+, are they spontaneous? So if you just put these together, then let's say you have copper 2+ CO2 mixed together. They're saying you mix them together, will there be any reaction? No, no spontaneous reaction because both are oxidizing agent. Okay, so you can't have any reaction. Okay, and how about copper and zinc? No, also because both are reducing agents. So both species, when mixed together, will not react. based on E0 cell value. Okay. So you can actually try to calculate lah to see it doesn't work. Yeah. So if you want, let's say if you want this to happen, both are because both are trying to reduce lah, so cannot lah. Yeah, if you have both things trying to reduce, no, sorry. Yeah, cannot. The E0 cell will be negative. Yep. So let's say you want this to happen. It will be this one. If let's say you want this, cannot lah, because okay, that's cannot. I don't know how to write, it just cannot. Then this one, yes, copper 2 plus and zinc. Because although, yeah, the zinc is this way. So the reduction potential, so this one will be the E0, the reduction part, right? This one will be the E0, the oxidation part. So you just write 0.34 minus 0.76 plus 1.10 volt, right? The overall equation. This way, for this one, you want copper, right? And zinc 2 plus, right? So you want the zinc 2 plus to be the reduction now. So you put minus 0.76 minus 0.34, it will be minus, so cannot. Okay, so that's how you use the E0 cell to predict spontaneous reaction. All right, you can just calculate the E0 cell to see. But for these two scenarios, you don't even need to calculate. Why? You cannot have both species reducing or oxidizing at the same time. Doesn't make sense. Okay, so last lesson we got talk about Gibbs free energy, entropy. I hope you can revise it on your own time. Very important concept in thermodynamics. So the concept of using the change in Gibbs free will also predict spontaneity. Yeah. So if you recall, if Gibbs free is less than 0, it's a spontaneous reaction. If change in Gibbs free energy is more than 0, it's non-spontaneous. So it's the opposite to E0 cell. E0 cell positive, good. This one negative, good. Okay, but if both is 0, then it's equilibrium. Meaning it will just exist in equilibrium. Not say reaction completed, but equilibrium. No more net change in the amount of the reactants and products. So this is the relationship between Gibbs free and E0 value. Okay, this equation must know. Okay, they may ask you to calculate, definitely. Okay, so delta G equals to minus NFE. Why minus? Because Gibbs free. Negative is good thing. So F represents Faraday's constant. It means that for every 1 mole of charge, sorry, 1 mole of electron, it carries this amount of charge. Okay, Faraday's is covered that. So we just use this constant value. Clear? Every 1 mole of charges carry 9650 coulomb. This coulomb. Okay. Then E0 is volts. Delta G joule per mole. Okay, how do you get joule per mole? Derivation. So N is mole times C per mole. Correct? And then you have voltage, correct? From the E0. So this one cancel off, becomes C times V, right? Okay. So the relationship between energy, charge, and voltage is this. Energy, which is measured in joules, is equals to charge measured in coulombs times the voltage. Okay, so energy equals to charge times voltage, which gives you energy. All right. Okay. Chi plus mole, why they cancel? But it's still per mole here. Oh, I forget. This one, right, is per mole. The E, right, is, if you remember, standard condition is per mole. So I think there is a mole here. So you still have a per mole there. That's why it's joule per mole. All right. Okay. Now, the per mole, right, is per mole of reaction. Oh, okay. The sign of delta G and delta E are opposite, obviously. A spontaneous reaction will have a negative Gibbs free, yes, and non-spontaneous has a positive Gibbs free. Okay. So, under standard condition, this is a summary. Okay, I will not elaborate. So, let's look at an example. So, you have this reaction Pb plus 2Ag plus to form this. So, first of all, you write the E0 cell first. So, identify what is the E0 reduction and oxidation. So, this is always the first step. And you take this minus this because it's negative, so it becomes minus minus plus. And then you sub into this equation. 2 times 96500 times 0.93, you get this. Number too big, so convert to kilojoules. Now, more exercise. So in the following questions, identify the relevant half equation that are mixed together, calculate E0, delta G, predict if it's spontaneous, and write any equations. Okay, fine. So Cl minus, so you write this, copy and paste from the data booklet, or they will give you lah. Okay, yeah, if it's something not in the data booklet, they will give you, or if it's something that, yeah, it's not even given the data booklet, then they will have to give you. They must give you. Okay, yeah, if not, but for this one, right, I think even if they don't give you, right, it's still possible to do it because we learn how to construct redox half equation for this one already. They will just tell you it's MnO4 minus acidic to form Mn2 plus. Then you have to balance with the, you balance this, you write this first, and then you write the H plus on the left hand side. That's what we did just now, the right constructing the redox equations. So the redox is here again. This is, I just shortcut now. And just minus, okay. And then Gibbs free, just use the formula. So it's minus, why is it 10 here? Because it's the number of moles of electron. Because if you look at the equation, right, this one is 10 because, right, if you write these two equations down, right, the number of electron transfer is actually 10 electron. That's why this is 10. So this is the number of moles of electron. You understand? So how do you get this is you look at how many electrons are transferred between them. Okay? Can? Yeah, so 5 and 2 multiple is 10. So it's actually 10. Okay? Just be careful of this thing. So you calculate delta G. Delta G is less than 0 spontaneous. And then the equation you just have to write according to the question demands. And then the observations is purple KMnO4 decolorized and chlorine will be formed because chloride is being oxidized and it will bleach the then litmus paper. That's why you cannot, that's why this is the reason why when we want to acidify KMnO4, right, we never use HCl because there will be a redox reaction. Clear? We always use like sulfuric acid because sulfuric acid will not have this reaction. Yeah. Okay, moving on. Br2 and Fe2 plus. Okay, so for this one, right, it's actually the gas ion, yeah, electrochemical cell, right? So you have, for this one, right, you have to decide very carefully what is being reduced and oxidized. So this has the highest, most positive standard electro potential. So it will be a plus 1.07. Then the other two, right, will just be the reduced one. But actually, you don't use this, okay, because it is not, because since you are going to, like, you know, Br2 going to reduce to 2 Br minus, right? Then the other species must be oxidizing. Yeah, but you are using Fe2 plus here. You say Fe2 plus, so you cannot use this. Because this must be oxidizing. So it can only be Fe2 plus. So this system is out. So you only use these two half cell. So it's plus 107 minus 0.77 because it's plus here, 0.30. Between them, these two more of electron transfer times 96500 times 0.3, you get this. So the overall equation is just a Br2 reduced to Br minus. So orange, remember bromine is orange, turn colorless. But then it doesn't turn colorless in the reaction mixture because the Fe2 plus becomes Fe3 plus, so it turns yellow. Okay? Okay. And because the Gibbs free is negative, so it's spontaneous. Okay, last one, I2 and H2O2 peroxide. So again, to decide what to use. All right. So in this case, there are three reactions that you can consider, but use only these two. Okay, because if you look at the E0 value, I2 become this one. That means that it will be, like you want I2 correct, to become I minus. Then die, you have to use this. So the other one have to be the one that, well, this is already the reducing one already. Then this one had to be the oxidizing one. So it can't be this one because the H2O2 is this side, not here. Here, the H2O2 undergo reduction. You cannot have two species undergo reduction at the same time. So one species will oxidize, one species reduce. Okay, always remember that. So it can't be that one, so it will be this one. So it's 0.54 minus 0.66. OO is negative. Negative. So it's not a spontaneous reaction. The Gibbs free is also positive. Then more example. Let me see any more to go. Okay. Let me see how much more. Okay, almost finished. Almost there. Yeah. It's just that they are, what example is quite a lot. What example a lot to help you, like, no more example. You can just use this in the practice. Okay, one more exercise. So these are the reduction half equations arranged in decreasing E0 value. All right. Taken from the data booklet, I think. Take reactions that are spontaneous and cross out those. So you just have to pick and choose lah. So for example, I2 and Fe2 plus, I go through some of it. I2, obviously I2 has to be reduced because I2 is the species here. So the other one has to be the one that is oxidizing. So you take this minus this is less than 0. So it's not spontaneous. Then for B, right, I minus and Fe3 plus, I minus here. So this will be the oxidizing one. The Fe3 plus is the reduced. So 0.77 minus 0.54. Yes, possible. Take C. Cl minus and Cr2O7, 2 minus. So this one has to be the one. So what I do here is you'll see, I will circle. This is a technique. I will circle them so that I know what I'm looking at. So this one must become this one, must be oxidized. So I must take 1.36. Okay, so 1.36. Sorry, oxidizing. So it should be done here, 1.36 here. Then this one is the oxidized. The reduced one is here, the oxidizing is here. So it's 1.33 minus 1.36. That's how I do it. The next one, D, I minus is here. So die circle here. Then O2, O2H plus. So it's here. All right. So it's reduced first. So 1.23 minus 0.54. More than 0. Good. Last one, I minus here. and H2O. H2O is the one that is reduced. So it will be here, this way. O2 and H2O this way, these two. So reduce 0.4 minus 0.54. So it will be bad, not spontaneous. So explain why iron 3 iodide does not exist in aqueous solution. Oh, it doesn't form because so with this E0 value, you answer this question. Iron 3 iodide does not exist because iron 3 plus, okay, here, is going to oxidize I minus to I2. And itself is reduced to Fe2 plus. So this is actually talking about part B here. So there is no reaction because, so how do you explain? You just say Fe3 plus oxidize I minus. So it won't exist in I minus. And Fe3 plus, when reacts with I minus, it will not remain Fe3 plus, become Fe2 plus. So FeI3 doesn't exist. As for the potassium manganate, should not be acidified. This one I didn't explain just now already. Yeah, using the earlier example. Yeah. But they don't have the MnO4 minus here, but it's actually it should be, oh yeah, this one is the earlier one, but potassium dichromate may be acidified because the Cl minus, right, it cannot react with this one. There's no redox reaction between them. The Cl minus can be oxidized by KMnO4 to Cl2, but it's not oxidized by K2Cl2O7. So you can still use HCl to acidify potassium dichromate, but cannot acidify potassium manganate. Then they say by potassium iodide solution turn yellow in the presence of acid. Okay, potassium iodide, this one you look at C. Okay, this one you look at E. Yellow because of the iodine, is it? The iodine formation, E. So E is it's D. Because O2H plus, this one. Acid, I forget the word acid. So acid H plus, so look at D. So what happened is that the I minus is oxidized to iodine by oxygen. So it will turn, so there's a reaction happening here. Because the E0 is greater than 0, spontaneous reaction. So you can actually use E0 value to predict whether reaction can occur based on thermodynamic principles. Yeah, based on that, can. All right. Of course, you also have to look at kinetic factor. That's why it comes to a limitation. So far, for those is based on, okay, just E0 value, but that is not the only consideration. So E0 cell is a measure of the position in equilibrium. So it will just tell you more likely or less likely, but it doesn't tell you how fast or how slow. So you could have a very energetically favorable reaction or thermodynamically feasible, but it may not be true all the time. All right, so for example, okay, if you, based on, E0 value, right, E0 cell, copper 2 plus can react hydrogen based on that. But if you really carry out in the lab, right, it cannot, no reaction. Why? Because the EA is too high. Okay, so kinetically not feasible. Okay, that's one. Number two, why sometimes based on the E0 cell, got reaction, but when I really do it, right, no, how come? Because the calculated E0 is based on standard condition, but whatever you are carrying on the lab may not be a standard condition. So if you try to predict E0 cell under non-standard condition, not valid. Yeah. So for example, this reaction, right, you could have a E0 cell of 0 volt, but it means that there's a reversible reaction where equilibrium occurs. But if you try to be funny, to change the concentration, right, of the ions, right, then there will be shifting of equilibrium position, right? Then you have some changes, okay? Sometimes, right, the another reason is, it could be there be side reactions. Like for example, insoluble ionic solid. So sometimes a non-spontaneous reaction may become spontaneous. Okay, for example, let's say this reaction, copper 2 plus and iodide. Okay, based on Enoch cell value, okay, so if it's copper 2 plus and I minus, right? So if copper 2 plus is a reduced one, always write like that. Then this one is oxidation one, because always circle. Correct, copper 2 plus, and sorry, not the it's the wrong one. It's this one, 2 plus, not plus. So this one to this one, then I minus, so this one copper 2 plus. Be careful. Sometimes may make careless mistake. Okay. Now, so you calculate the Enoch cell, it is supposed to be not spontaneous because it's negative. But then sometimes, but in some cases, right, like this, right, you form a copper 2 iodide, which is a cream precipitate in brown solution of iodine. Why is that still a reaction? Because copper 2 iodide is insoluble. So what happened is that the lattice energy, right, release. Lattice energy is when the gaseous ions react together to form the product. So the energy release, right, will favor the reaction because there's energy release from the ions come together to form the product compound. So due to this side reaction, right, which is the precipitation of copper 2 iodide, then your copper 2 ion become very low. Then when the copper 2 plus ion become very low, your Enoch cell become larger than this. Okay, so this will increase. All right. So your Enoch cell become larger than negative 0.39 as calculated here. In fact, it will be beyond, it will increase until greater than 0 and the reaction becomes spontaneous. Okay. Okay, last part is the fuel cell and batteries. Okay, so fuel cell is the electrochemical voltaic cell, which convert chemical energy of a continuous supply of reactants into electrical energy. Okay, so a fuel is supplied to one electrode and oxidant to the other. So at the anode, right, the fuel is oxidized and electrons are released. At the cathode, the oxygen is reduced by electrons received from the external circuit. Okay, so always anode oxidation, release of electrons. Cathode oxygen is reduced, reduction, electron received. And then they actually produce energy. So this is the hydrogen oxygen fuel cell. And what is happening is, okay, the electrolyte is KOH alkaline. Then at the anode, so this is the input, hydrogen and oxygen. So at the anode side, the hydrogen reacts with the OH minus. It undergoes reduction. Undergoes oxidation, it forms water. So OH minus, H, you balance by the water. At the cathode side, the oxygen and water reacts, undergo reduction to form OH minus. So there's regeneration of the alkaline actually. Okay, so this one looks very familiar, right? This is actually the opposite of the famous reaction at the anode, where you have the oxidation of OH minus. So the opposite happened. But that one is for electrolysis. So the overall equation, just balance these two, you'll get this one. It's just water formation from hydrogen and oxygen. So if you copy down the Enoch data, okay, so this one would be 0.4. Okay, then for this one will be minus 0.83. All right, but if you change it to, so just roughly know the equations lah. Okay, you need to know. All right. If you change the electrolyte to something acidic, like H2SO4, then the hydrogen will be, be different. Some will be like SHE, right? So 0 volt. O2 4H bar is a different voltage reading. So this one will be plus 1.23 volt. Okay, so the O2 on the cathode side will read, because it's not alkaline, it's H plus. If you change the electrolyte, then it will be 4H plus. So this one can be acid also. Okay, so 4H plus 4E minus form water. You gotta remove this, very confusing. Okay, then you have E0 cell plus 1.23 volt. So despite the difference electrolyte used, your E0 cell will still be the same. Yeah, it will still be the same. So what's the advantage of having the hydrogen oxygen fuel cell? Hydrogen oxygen, because the input gases are hydrogen oxygen, you are able to obtain maximum power with minimum weight and volume. So with less weight and volume, we can get a lot of power, which is useful for spacecraft. We need to travel a longer distance. High efficiency of conversion of chemical energy to electrical energy, like up to like 70%. You don't lose a lot of energy. The fuel cell won't go dead because you can actually supply the reactants continuously, and products can be continually removed. Yeah, but for battery, like at your home, right, it will just stop working when the electrode material use up. But here is continuous, so this is another advantage. High efficiency, maximum power, supplied continuously reactants. And of course, the product is non-polluting. In fact, you can use the water to drink and wash. So in the US space laboratory and spacecraft, right, sometimes the astronauts, they will actually use the water and not waste it. However, this advantage is of course expensive because you really need a lot of the electrode is actually platinum, and some more it is not the usual type of platinum. Yeah, really very really finely divided. Then you have to use platinum is used as a catalyst actually. And it's not the usual way you use platinum as electrode, but you use it as catalyst. Then catalyst will become poison because over time, the active site, so-called, will be accumulated with impurities. Then it will not function well. Then it will decrease the efficiency over time. So efficiency will be compromised long. And for this to happen, you need a high temperature. High temperature means more energy you need to get from somewhere. And it's not safe because hydrogen is potentially explosive, especially if oxygen there also, right? So there could be explosion. So there's risk of the people dying inside the spacecraft. So, boom. Okay. Then, okay. 2 fuel cell using ethane, but different electrolytes. So just more examples. So if you use ethane, electrolyte is H2SO4. So at the anode, there's no need to give the, how should I say, give the E0 value. You just have to write the equation. So, so at the anode, right, this one is just an example for you to make reference. You just need to understand that different electrolyte will result in different reactions at the electrode, but the overall reaction is still the same. That's the whole point. So ethane, you can also use electrochemical method to actually utilize ethane as a fuel instead of just combustion. This is another way, interesting way, not just combustion, then you form CO2 and water, right? But it's actually the overall equation is still like combustion, but you can still use the electrochemical cell to do it like this way. So C2H6 plus water. So it forms CO2, H plus, and electrons. It's a reduction, oxidation. Then at the cathode, you have oxygen, react with H plus, reduce to form water. Just combine these two together, you get this. Okay, no need to memorize this lah. Okay, just for your information. So same thing, if you change your electrolyte to sodium hydroxide, you have OH minus, you form CO2 and water, O2, water, reduce to form OH minus. Okay. So the alkaline part is quite similar to this also. Yeah. And for the acidic one, you realize that for the anode, right? Okay, they always have, if it's alkaline, they will add the OH minus. If it's acidic, right? For the anode, right? You not add H plus on the left hand side. It's actually add water or don't add anything here. It depends. Yeah. You add water to produce the H plus. You return back the H plus to regenerate it. Yeah. Okay. So last one, just for your reference. Okay, you can read yourself about zinc carbon dry cell, another type of cell. Yeah. Basically know how to write the equations. All right. And the use of the materials lah. Okay, alkaline dry cell. The different type of batteries. For reference, I just good for you to read, because even they'll give you the context. But it's good for you to just read up. Then this part is for the traditional car battery. What happened during discharging and charging? Yeah, it's like your handphone, right? You recharge it and then discharge when you use it, and recharge, charge, discharge, charge over time, right? Yeah. So for car batteries, right, it can be recharged up to 800 times maximum. Yeah. But the rest is like how you can improve the cell by looking at smaller size, lower mass, higher voltage, longer lifespan, greater reliability, quicker recharging. These are the considerations when we want to develop better cell. Anyway, there's a whole hoo-ha about fuel cell nowadays. Green energy. Okay, so nowadays, not just this, but also how is it more environmental friendly, how we can reduce the carbon footprint, etc. Okay, so these are the emphasis of current trends. Yeah, not just looking at more efficiency only. Of course, efficiency very important. If you can make something green and very efficient, you are good for it. And it's not too expensive. Yeah. And also must look at a lot of factors like this, just to let you know that in choosing the correct battery, the good battery, you also have to make sure that it's not so noisy, you see, and easier to maintain. Yeah, all these things. Electric car is good, but then the range is still quite limited. Your speed cannot exceed 80 for now. Maybe can already, not sure. The latest research maybe can. And they are quite heavy, so people don't really like electric car, heavy battery, bulky, and recharging time can take, but now they improve already. Now it can take a shorter time, but before that, it was not very good. Okay, but so the criteria for batteries for electric vehicle, I thought about this because they keep on talking about it. Yeah, so high energy density, long life, and good durability, reliability, and quick recharge. Okay, so that's it